Okay, why don't we get started? Welcome back, and we will today proceed forward with new material concerning Chapter 4, which is the network layer. And in this version of the text, the 7th edition of Ross Computer Networking Top-Down Approach, they split the network layer into two components, one called the data plane and the other called the control plane. And I'll explain a little bit in today's module about what that means. First bit of information on the administrative side. Homework 3 has been posted on the course Blackboard, and that will be due on the 31st of March 2020 at the usual time, which is 1 second before midnight. So please make sure you get on that right away, especially because the delivery method for the course is online. You will want to get started on that as soon as possible. Okay, so let's start out with an overview more generally of the network layer. And so the goals of Chapter 4 in the text is to look at principles behind the network layer services, and the focus of Chapter 4 is on the data plane. So we'll look at service models, we'll look at forwarding versus routing, what the difference is, how a router works at an architectural level, and look at generalized forwarding and how that manifests itself or is implemented on the internet. And so what is the network layer? Certainly we talked a lot about the transport layer, and it's responsible, the transport layer, for getting a segment from the sending host to the receiving host. And on the sending side, it encapsulates segments into datagrams. And so the transport layer, as we very well know at this juncture, the transport layer sits right above the network layer. And so when the transport layer sends a segment, it sends that segment into the network layer, and that transport layer segment, as well as the transport, which includes the transport headers and the transport layer just payload, that's all encapsulated and put inside of a datagram. Now, of course, that datagram at the network layer includes new header information that is meaningful to all the network layers across the network. Then on the receiver side, the network layer on the receiver side takes its datagram and sends the segment contained inside to the transport layer above. And so the network layer exists in every single host, as well as all of the interior components, namely the routers. And a router only implements layer 1, 2, and 3, physical, data link, and network layer. And therefore, in the literature, you'll often hear the router referred to as a so-called layer 3 device. And so what does the router do? It examines header fields for network layer header in all of the datagrams that pass through it and take action based on what information those fields contain. And so when we talk about the unit of data at the network layer, we ascribe a new name to it, and that name is called a datagram. And so here we have edge devices. We have a server on one end of the network running on an enterprise network, and we also have a laptop running on a mobile network. And you'll see here they have all of the 5 layers: physical, link, network, transport, and application layers. And we're going to highlight here this network layer because, of course, certainly that's what this chapter refers to or discusses. And so we also have all of the routers that are dotted about the internet, and certainly we have our switching fabric in the center, but we also have gateway routers that connect each one of those networks through an ISP to the switching fabric. And you'll see here at each one of those router devices, it supports 3 layers, or implements 3 layers, namely physical, link layer, and the network layer. And so we take our application layer message, pass it into the transport layer. Someone calls RDT send from above. That transport layer adds its header information, and the payload contains the message from the application layer. And then that transport layer segment is passed down into the network layer. So once it makes its way from the network layer, it goes up and down the stack for each one of these layer 3 devices or routers until eventually it's delivered to the destination endpoint and makes its way up the 5-layer stack implemented on that destination endpoint. And so, as you can see in this figure, you have network layer at every single host as well as every single component on the network, and therefore the network layer exists everywhere on the network on all the devices. So what are the network layer functions? Functions The network layer's functions are twofold, namely forwarding and routing. Now, forwarding is the moving of a packet from the router's input port to the appropriate output. And so a router, recall, is a so-called store and forward device. And as such, packets arrive into the router through its inputs, and then the router examines that and sends it out, transmits it out some output. So the forwarding is the moving from input to output, and there's a decision that's made that we'll talk about. But the routing is more of an aggregate construct. It's the determination of the routes, i.e. the set of hops or links traversed and routers over which that datagram passes in getting from the source to the destination. Now, that consideration takes in a lot of information concerning the links, and we'll talk about that. And a routing algorithm is responsible for incorporating all of this local information about traffic on the network and making this routing decision. And that's an end-to-end consideration. And we'll talk about the major algorithms for doing that, distance vector routing algorithms and so-called link state algorithms, routing algorithms. And so the analogy used in the book, and they like to make a lot of analogies in the book, the forwarding function of a router is the process of getting your car, if you're maybe taking a road trip, getting your car through a single roadway interchange. So you go through one cross section along a segment of road. And the routing process is the process of planning an entire trip from source to destination. Now, certainly that trip from source to destination is going to involve a number of passes through various interchanges along the way. And that's exactly what happens in routing. And so again, the forwarding is like passing through an interchange, and the routing is like planning the entire trip end to end from the source to the destination. You have to traverse through a set of interchanges in order to get from one source to a destination. So let's take a look at the data plane. The data plane, it's local, and its function is on a per router basis. And with the data plane, the task is to determine how an arriving data plane, an arriving datagram, how a datagram arriving on the router input port is forwarded to the output port. Now, there's a switching function that's involved, and the piece of information that is used to determine where this datagram that arrives, where it goes, on which output port it goes out, is a piece of information, namely the internet, for the address, the IP address. So the IP address is a number, and we'll talk about its structure, and this number is encoded in binary, and based on that binary value, a determination is made using a table to look up which output that datagram with a certain set of addresses should be forwarded. And so here we have a packet in the figure that's arriving into a router. It comes in on the input port, and then that address information is looked up into a table, table's consulted, and depending on the value of that address, it will either send it out port 1, port 2, or port 3 in this example. So let's assume, let's say port 2 is going to be the port out which this datagram is transmitted when it has a certain address, 0111, then of course it'll get transmitted out of port 2. And so there are a bunch of things that happen. You have the arriving datagram, you have the examination of the address information, the lookup in a table, and that table associates output ports with address ranges, and then the actual forwarding based on that match to see which number is in that router is associated with which output port, and then the physical forwarding of that output port. So that's the so-called forwarding decision, and that forwarding function or forwarding decision is referred to as the data plane, and that's a local thing for your router. So then when we broaden our view and we talk about the control plane, that's a network-wide type of operation. And so the control plane has to take into consideration all of the link information across an entire network. It inputs that information and then determines over which set of routers, over which output links that message or that datagram should be forwarded in order to make progress along some pathway through a set of links and routers to get from some source to some destination. And so the control plane determines how a datagram is routed among routers along the end-to-end path from the source host to the destination host. So there are two approaches for the control plane. One is so-called traditional routing algorithms, and in a traditional routing algorithm, as we'll see, it's implemented entirely in the routers, and they exchange information with one another. And then there's so-called software-defined networking, or SDN implementations. Now, these SDNs use an API, web-based API, to abstract, or service API to abstract the functions that otherwise would have been made at a single router. It's made in some server. And so then each of the routers send information to the server. That high-level global end-to-end set of considerations are analyzed, and then the resulting solution or path or route is determined, and then each one of those forwarding decisions that is each router is responsible for, those pieces of information are sent to all the individual routers by the server. And so here we have the centralized control, but this control plane includes this notion of a server where the computation of all these global considerations, i.e. The routing path from source to destination endpoints is made. Okay, so there's the control plane. And let's take a look at the first approach, the so-called traditional or older approach, where you have a per router decision that's being made. And so here in this, there are a bunch of pieces of information. We have our datagram arriving into the input port on the router. And inside of this router, if we kind of blow that up, you have what's called a local forwarding table. And this is the table that we referred to. This local forwarding table has a set of addresses, and these addresses are pulled from the address field of the network header. And these addresses are associated with ranges of numbers, and if that address in that packet resides between a certain range of addresses, then it's output to a particular port. And so, for example, and this is sort of a simplified example just to illustrate the point, let's say this packet arrives and its address information is the number in binary 0111. Well, we look up 0111 in the table. We see 0111, and associated with 0111 address is port 2. So this datagram is forwarded out port 2. Now, not only is that first router doing this, every router on the network has a forwarding table, and that forwarding table makes that forwarding decision and is essentially implemented as a table lookup mechanism. And so there's another process that's called the data plane, because that data plane is the entity that informs the switching decision, right? That table encodes what range of addresses will cause that datagram to go to a particular port number. And that forwarding decision is collectively called the data plane because it traffics in data, how you switch data between the input and some determined output port as encoded by these local forwarding tables. So then we also have a control portion. In the traditional approach, we have a process that's running, and a router is nothing more than a specialized machine or host. And this router has a process that's running called the routing algorithm. Now, the routing algorithm makes the determination of what the forwarding table should contain as a result of exchanging information with other routing algorithms across the network. And so once that routing algorithm has converged, it's done recalculating routes, it then takes the responsibility of that route from the perspective of that particular router in which the algorithm resides. It downloads that forwarding table to set those switching decisions, those forwarding decisions for that particular router that implements that router's part of the end-to-end path calculated by the routing algorithm. And so these routing algorithms, where do they get this information? This information has to do with the amount of traffic associated with each of the links on the network. Now, routing algorithms have neighbors, and a neighbor is nothing more than another router that shares a link with some other router. So here, this first router, it is a neighbor of this second router. And if you look at the network diagram, this first router and this second router, they share an edge here, and that edge is that edge from port 3 on the first router outgoing to its neighbor. And so those routers exchange local information with one another, and that information encodes the traffic conditions on that link. And given that information, they compute what the optimal route is. If you look at this graph, well, it's a connected graph, and so if you exchange information local information with each one of your neighbors, eventually neighbors exchange information, and each neighbor converges onto what the link information is. They all gain the same understanding over time of what the link status is for all of the edges on the network. And we'll talk about what that information is. There's two ways of doing it, one called link state, one called distance vector routing algorithm. And we'll get to that when the time is appropriate. Okay, any questions? Okay, so this logically centralized control plane, it's distinct. Typically, in this software-defined networking, you have a remote machine called a controller, and it interacts with so-called control agents. And this is a different approach that's related to, but not the same as the localized control decision. So here we have a bunch of routers, and each router, again, is nothing more than a host. And instead of running the routing algorithm, each one runs a control agent. And this control agent is going to take its directives from a centralized machine called the remote controller. And so in essence, what software-defined networking does is it abstracts that idea of a routing algorithm, pushes all of that onto a server called the controller, and now this thin piece of software running on each router called the control agent, it's like this very simple bot, if you will. All it does is it takes commands from where all the smarts are, this controller, and it just effects those changes. And so one of those changes is to go ahead and update the local forwarding table. So here we have, again, our first router, and each router has a control agent in that, and that's in contrast to the routing algorithm. And so these control agents exchange information with the remote controller. One piece of such information is the local forwarding table. So the neat part about this is that now using a service API calling into the remote controller, you can now configure flows and paths, if you will, affect it as part of your computation, affecting the data flow that your application needs, which is kind of nice. So now with this programmatically, your program contacts the controller and can effectively cause it to set up the types of data flows that the application needs. It's a really, really neat change to how routing is done. Okay, and so these control agents can download new local forwarding tables from the remote controller. And so the data plane down below the dotted line consists of, in the software-defined networking regime, consists of the routers and these control agents. And these control agents phone home, as it were, to the control agent. And the control agent runs a bunch of algorithms for things like establishing paths and routes and all kinds of things. And that's called the control plane. Okay. So there are various service models that you can have for the channel that transports datagrams from sender to receiver. So, for example, you can establish certain pathways. You can have fault-tolerant pathways. You can have multiple pathways. All sorts of things you can do with this idea that the computation first sets up the flows using the controller, centralized controller, and then restores resources, perhaps consumed, i.e. bandwidth for certain flows, restores them back for general availability. And so what sort of services could you have for individual datagram? You could perhaps set up something like guaranteed delivery. Maybe there's delivery with no more than a certain upper bound on delay. And for flow control or flow of datagrams, you could have in-order delivery. You can perhaps maybe set up guaranteed minimum bandwidth or have restrictions on changes on the amount of interspacing between the sends of the packets. And so I'm not going to talk about network layer service models. Let's focus or segue to what's inside of a router. And so for a high-level view, here we have a general router. And a router consists of a number of high-level components. And so we start out, we have a high-speed switching fabric. And a switching fabric is nothing more than some custom silicon, typically like some ASIC. And its job is to get bits from one channel that's coming in to some output channel that's going out. All of this switching fabric is controlled by a processor, a specialized processor, the routing processor. So this high-speed switching fabric kind of acts like a specialized I/O device where the routing processor controls the setup of what input is going to be mapped to what output, as well as actually turns on the switch and turns off the switch. Okay, so then we also have a bunch of so-called router input ports, and these input ports are where the datagrams come in to the system, and the output ports are those entities or components out which data is transmitted when it's leaving the router. Okay, and so the forwarding data plane refers to all of the switching fabric and the input ports and the output ports, and that's the physical setup that will establish circuits to connect data that's on the input ports to go or leave this device through the output ports. And so this hardware operates in nanosecond time frame, 10 to the minus 9. It's really, really, really fast. And as you can imagine, it has to be fast because if you want to get 10 gigabit and 1 gigabit data speeds, this thing has to be really fast, and it's usually on the order of 10 to the minus 9 or nanoseconds. Conversely, the control plane consists of the routing processor, and the routing processor makes all of the path evaluation decisions, and it doesn't need to run as fast, but it has to be, relatively decent speed or performance. Now, this routing processor runs all of the routing, namely the exchange of messages and the computing of optimal paths, the management of the control plane, which is software that allows you to establish these pathways and download the forwarding tables. And these things usually operate on milliseconds. Certainly, it's a lot slower than the data plane, but then again, you're not running this continuously on live data as it arrives into the router. Okay, so the router processor is responsible for downloading the local forwarding table. So if we were to look more closely at the input port consists of three major functional blocks. One is the line termination that deals with the physical layer, the transmitting and receiving of bits as signal energy. Then we also have this blue block, which is the stage that deals with the data link layer protocols. Now that is the sending and receiving messages between machines that are on the same local network, be that wireless or wired. And then lastly, we have forwarding and lookup, which also has buffer space for queuing. And these lookup stages implement a decentralized switching. Namely, they act in parallel relative to the output ports and the other input ports. And so what happens with the decentralized switching? It looks at the header field values, as we talked about before. It looks up the output port using forwarding table entry for that match for the address information. And then it sets up that pathway and actually sends that bit information across the switching fabric. Now, the goal is to complete the input port processing of data at so-called line speed, meaning at circuit level speed. And that's how you get it fast to work on the order of 10 to the minus 9 or nanoseconds of time. And so if you have a lot of datagrams arriving at your input port, this input port will queue them. And this is where the queuing delay comes into play. And the queuing memory is actually here in this red stage of the input port. Now, on the other side of this input port, you'll see the switching fabric, and that switching fabric is that network, if you will, of interconnections that will transmit that bit to one of the output ports for going across the wire ultimately. Okay, and so this lookup happens in a number of ways of doing it. One's called destination-based forwarding, and this is forwarding based only on the destination address, the so-called Internet Protocol or IP address. And this is a traditional way of doing it. And then there's generalized forwarding. It's based on any set of header field values. Now, it's more typical to do destination-based forwarding, but certainly generalized forwarding is also very popular. Is not, it's more rare, but not as common, but certainly it's very doable. Okay, so here's an example of the forwarding table, and we have an encoding in binary of four numbers, and these numbers are each 8 bits long, and as an 8-bit number in binary, you can represent the value from 0 to 255. Now, as such, when you have a value from 0 to 255, this is represented more simply in decimal as a so-called dotted quad. And as a dotted quad, we have a number, binary or decimal equivalent, and we write out that number, each one of these 8-bit digits, as if it were in base 10, and separate those digits those 8-bit digits by dots or by periods. And so this is a so-called dotted quad, and this is the structure of an IP address. And so when you see an IP address like 192.168.1.14 or maybe 10.0.1.5, each one of those decimal numbers represents an 8-bit. If you expand them out to 8 bits, it represents one of these 8-bit regions that collectively correspond to the address. Now, you'll notice here this consists of 4 8-bit words, so that's a total of 32 bits, and so we often call this a 32-bit address. Okay, so here we have 2 addresses. For example, the first dotted quad, that's 200, and then we have 23, and then we have 16, and then we have 0. And so this represents the bottom end of the range of addresses associated with the output on port 0 or link interface 0. And then we have 200, we have 23, 23, 255. So that means if your binary encoding of your IP address falls within this range of 200.23.16.0 and 200.23.23.255, then it's going to transmit out interface 0. But certainly, you'll notice these things are sequential, right? What comes right after this number is this number, and they don't always have to be sequential, right? You can have them asequential, and we'll explain how that works when we talk about max prefix matching. Okay, so this longest prefix match scheme says that when you're looking for the forward table entry associated with a given destination IP address, you're always going to use the longest prefix, the longest binary number string that matches the destination. And that essentially allows you to define this idea of smaller networks within a larger network, where network is just nothing more than a range of addresses. And so here we have an example of that. We have destination address ranges, and this star or wildcard means it doesn't matter what the other stuff is. It's going to match these first 8, 16, 18, 20, these first 21 bits. And so here we have this pattern. I think that's, let's see, it's 200, looks like 23, and another part of the 23, but the 23 isn't really filled in. These last 3 digits here, least significant of the 8, the third dotted quad, those are all wildcards. And so here, if we look at these 3 addresses, well, the first address is defined in 8, 16, 18, 20, 21 bits. The next address is in 24 bits, right? And then this last address, that's defined in 21 bits. So suppose we have this following destination address, and if we were going to do the match, well, we match it against the longest prefix. These are called prefixes. And so here we have this pattern matches for these first 21 bits with this topmost address. But if we look, let's see if we can look a little further. If we have this address, well, it certainly matches the top one, and everything else is wildcard. It doesn't match the bottom one, right? Because we have that 1, 1. This is see 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1. So it's not going to match the third one, and then this second one is also not going to match because it has 0, 0, 0, 1, 1. This is 0, 0, 0, 1, 0. So this first destination address would be transmitted out link 0. Let's take a look at this second destination address on the bottom here. Well, if we look at this third 8-bit number, or the third quad in the dotted quad, well, we have 00011, 00011. We have 00010, 00011. Well, it's going to match either this entry in the table, second entry, or the third entry. But if we look at the other bits, well, it has 000, 000, because that is the longest prefix, right? Instead of being 21, it's let's see, 8, 16, 18, 20. Instead of 21, it matches 24 bits, right? So because this match matches more bits for the second entry than for the first entry, we're going to transmit this out of link 1, because that's the link interface associated with the match for the pattern that's in the second row. Okay. All right. So um, why longest prefix matching? Because it allows you to pick up and move sub addresses, and we'll see an example of that in the pages slides that are coming in the future. Okay. So longest prefix matching is often used as a special type of memory, so-called content addressable memory, which does very fast lookup and matching. And I won't get into the details of that. It's beyond the scope of this class. So let's take a look at the switching fabric. And the switching fabric is that mesh, if you will, of silicon circuitry that connects the input ports to the output ports. And so the switching fabric is responsible for transferring packets from the input buffer to the appropriate output buffer, and this determination is made by the local forwarding table through this content addressable memory mechanism. And so the so-called switching rate is the rate at which packets can be transferred from the inputs to the outputs, and the faster the switching rate, the faster your router can push data out, right? Because the switching rate determines how quickly you can get packets from the queue at the input port to the output port. Now, this is often, when you look at the switching rate, it's often measured as a multiple of the input-output line rate, right? Because you have multiple lines, and the switching rate is the aggregate of all of the switching performance for each one of those input to output port pathways. And so there are three basic types of switching fabrics that we'll talk about only at a high level. One is using memory. You can absolutely use computer memory as your switching fabric. By today's modern standards, it's not a very good mechanism, but the early routers in the very early days used memory. It was just a computer on which you installed routing software. And the only thing we'll see that it qualifies you to be a router is you have to have more than one network interface or network card, and boom, you're a router, right? Quite easy. So we have memory. We also have a bus, kind of like the bus on a system. It's a high-speed interconnect that all these input ports and output ports connect over. You can address things and send data from one input port to another. Same way a peripheral, like your disk, can send data, for example, to your memory, okay, your RAM. So we also have the crossbar switch, and the crossbar switch is a little bit special. It's more specialized than the bus, and they usually implemented as custom hardware. Crossbar switch is such that you can have more than one input port sending data to an output port at the same time, as long as they're not sending data to the same place. So for example, if this top input port was sending data to this middle output port, at the same time this middle one was sending to the right hand, and this bottom one was sending to the left hand output port, they could all send at the same time concurrently if the source destination pairs are different from one another. And so that's one of the benefits of the crossbar. And one thing you'll see, well, we might be thinking, gosh, well, why would you ever have it with memory? Well, all of these old methods for implementing switching fabrics, they're still there, but we still have to study them because sometimes history repeats itself. Okay, so let's take a look at switching using memory. And the first generation routers use this approach. And in fact, you can download router implementation distributions of Linux, special distributions where you download it, install it on your computer, and you're up and running with your computer as a router. Now, of course, you want to be careful if you do this, because if you advertise your computer as a router, a lot of traffic is going to find its way across your machine. And so in the first generation routers, these were nothing more than traditional computers where the control plane was under direct control of the CPU, right? So the CPU or processor implemented the control plane function. And so what happens is a packet would come in and it would be put into a system's memory. So you were limited in terms of switching rate by the bus bandwidth associated with memory I/O operations. And so the speed limit was limited by memory, and you cross the system bus twice in order to do your switching. So you go from the input to memory, across the bus to memory, and then from memory across the bus to the output port from one interface to the other. So your packet will come in, go into memory, it would come in, queue it up in memory, and then it would go out memory to the output port for transmission, and you're done. So let's take a look at the bus. Now, the bus was a big improvement. And a bus, because it is highly specialized for fast transfer between devices, essentially your datagram goes from input port memory, this buffer, this queue, to the output port memory using a shared bus. Now, of course, because this is a shared resource, you're going to have bus contention, but it is nonetheless much faster than memory, and you can typically get about 32 gigabit per second, at least as of the writing of the book, bandwidth, switching bandwidth for speed. And these are typically used for access networks and sometimes for enterprise networks, the routers that use switching via bus or bus-based switching. So then we move on to switching fabrics or interconnects using crossbar switches. Now this overcomes the issue of bus bandwidth because you have multiple pathways and you can do that concurrently. Now there was a company called Banyan which pioneered the so-called butterfly network and crossbar switching network, and they were bought by Cisco a long time ago. And so that Banyan technology is used in Cisco routers. And this crossbar approach was originally used to connect multiple processors together in a multiprocessor system. So they were envisioned in the beginning for doing high-speed data switching frequently. It's an advanced design. It can do fragmentation and all sorts of reassembly of things through fixed length, so-called cells. So it takes the data, chops it up into its own custom unit of data, which it then sends across the switches. Enterprise networks typically use crossbars, at least as of the writing of this book, and it can switch at a rate typically around 60 gigabit per second, which is pretty fast. Okay. All right. So let's take a look at the queuing at the input port. Now, we said that the input port has some queues, and if datagrams arrive at the input port faster than they can be switched out, they're going to be queued. So they're going to wait in some buffer space that's inside of the input ports. And so you can have queuing delay if a packet waits too long to be transmitted because it has to be at the front of the queue or the head of the queue in order to be transmitted to the output port. So there's something called head of line blocking. And head of line blocking can occur for a number of reasons, but this is a particularly interesting one. Suppose we have this blue packet waiting behind the red packet, and then in the center input port, we have the blue packet, and it wants to get switched to this blue output port. And then let's say we have this red packet here. It wants to get switched to this upper output port at the same time that this other packet from the top level input port also wants to get switched to that first output port on the right. Now, certainly, if this resource is currently occupied, meaning it's currently receiving data, you can't switch another packet if that resource is taken. And so there's something called head of line blocking. And what this head of line blocking says is that the queue datagram at the front of a queue prevents others in the queue from moving forward. So that means that because these two red packets are in contention for getting switched to this same output port, well, if this bottom input port, if this head of line or head of queue element or packet is being blocked, if you will, from being transmitted to this output port, well, this green, it doesn't need to contend for that blue output port. It could go straight to this green output port if it were at the head of the line. But it's not at the head of the line, and therefore has to wait for this red datagram to be transmitted to this red output port. Now, this red datagram at the bottom, it can't be transmitted if that output port is currently occupied because this top red input, this red datagram at the input at the top, is occupying that resource. And so this is called head of line blocking, means that a datagram at the front of the queue prevents others in the queue from moving forward. And you'll see here, the green doesn't even contend with all of those other datagrams trying to get to the red output port. But yet it has to wait because the datagram in front of it is blocked. Okay, so one time step later, let's say this head of line red datagram, it now gets transmitted and queued at the red output port. So now this other red one is now free to get transmitted across the switching fabric to the red output port, and then this green one can make its way across. take a look at the output port. Now, the output port also does queuing. And because it does queuing, you're going to need buffering. So you're going to buffer in two places in the router. You're going to buffer on the input port as datagrams arrive, and you're also going to buffer on the output port as datagrams are transmitted across the network, leaving the router. So you can certainly have more than one datagram getting switched from an input port, forwarded from an input port to an output port. And because of this, you might need, or the issue or circumstance might arise where you're going to need to store or buffer those datagrams that make its way off the switching fabric. Because remember, the switching fabric is also very, very fast, right? And it's not atypical for a switching fabric to be faster than the ports that are on the input side as well as the output side. So nonetheless, if you get more datagrams than you can handle as an output port, you're going to store them, and they're stored in a buffer. And so the output port also consists of these three components. It has the buffer that implements the queuing. It has the link layer protocol portions, and it has the line termination for the physical layer constructs. Okay, so I was going to make a comment about net neutrality, and net neutrality has to do with a preference for data. And when you prefer data, you're making a selection as to which datagram is going to be transmitted out the output. Now, net neutrality argues that when you don't have a preference for data, then you're not ruining the flow, if you will, from end to end. And some would argue that, well, you need to make a preference because data results in money. And if you're trafficking in lots of high resolution data like Netflix, then you should have to exchange money, if you will, or work out agreements because your data is costing someone else money because it's causing queues to build up, and you have to build out that infrastructure to handle all of that traffic. And so when you buffer because datagrams are arriving from the switching fabric faster than you can transmit them out across the wire from this output port. And so you need some way of selecting then which datagram is going to be transmitted. Now, you could certainly use the default queuing behavior where the head of line item in the queue is what gets selected for transmission, or you could have some other criterion that you employ for selecting them. Now, of course, that is part of the issue with net neutrality, right? What do you use to determine which of these datagrams get selected for transmission from the buffer? Now, do you stamp these packets with, this person is paying for the gold plan versus the other one's paying for the bronze plan? So therefore, if you're going to make a scheduling decision to select a datagram from the queue for transmission to the output, I'm going to prefer selecting things that are stamped as being the gold plan, the gold data plan. Now, of course, this has the potential of ruining the quality of things on the internet, but the jury's still out, remains to be seen. I'm not going to argue for or against one way or the other, just letting you know that net neutrality is a very important concept. All right. And so certainly where you lose packets is at the buffers, right? So if the datagram comes to an input port and the buffer's full, it can get dropped. If a datagram leaves the switching fabric and enters the output port and sees that that buffer is full, it can also get dropped. And the scheduling here, based on various priority schemes, is how you would prefer certain types of data as it pertains to the net neutrality argument. Okay, so let's take a look at output port queuing. Again, you buffer information when the arrival rate at the switch exceeds the output line speed. And the output line speed is to get from the output port to the network, transmit onto the wire. And the switching rate refers to the switching fabric, the speed at which data makes its way from the input port across the fabric, switching fabric, to the output port. And so you're going to get delay and loss at the output buffer as well as at the input buffer. And so there are certain schemes for how you select the amount of buffer space. And in fact, when you buy high-speed routers, one of the things you pay for is the amount of router memory. Now, this isn't the same as going to an online vendor and getting another memory stick for your computer or memory module. This is very highly specialized memory tuned specifically for a router, and that adds to the cost. So when you see a router that's an enterprise router that's very expensive, part of the reason for that is that you have very custom, highly specialized, very fast memory on board, and that costs money. Okay, and so the scheduling mechanism is the means by which you choose the next packet from the output port queue in order to decide which one gets transmitted out the outgoing link. And so one way of scheduling is using first in, first out, or FIFO scheduling. You basically send them in the order that they arrive to the queue, because those datagrams that were sent earlier are the ones that tend to be closer to the front of the line. And so what are some real-world examples of other scheduling disciplines? One is to drop from the tail. One is to randomize the dropping of a packet. Another is some other priority-based scheme. So you have a queue, waiting area, packets arrive. You have a link, which is the server, and then that packet departs. In fact, there are mathematical models for how you analyze queues and look at the number or size of the lines in the queuing area and so forth to arrive upon optimal number of services, optimal queue size, and things like that. So I'm not going to talk too much about scheduling priorities. That's in the book, but I won't hold you responsible for that. So let's end with IP, Internet Protocol. Let's look at the network layer. And the network layer consists of three major behaviors, or three major components. One is the routing protocol, and that's responsible for the selection of the end-to-end paths. And there are some popular routing algorithms: RIP, Route Information Protocol, OSPF, Open Shortest Path First, and BGP, Border Gateway Protocol. Now, each one of these routing protocols is responsible for exchanging information with other router instances, and then computing that end-to-end path, and then downloading the resulting forwarding table into each of those routers. It is also responsible for the IP protocol, and that includes the addressing convention for int IP addresses, the format of datagrams of the actual data, and also handling standards for packets. There's also error reporting called ICMP, Internet Control Message Protocol, and that's for error reporting and looking at the status of routers and for signaling various things about the network infrastructure as it pertains to layer 3 or the network layer. So this is the IP datagram format. It's 32 bits wide. We have the version field for the IP protocol version. The two values you can have there is 4 for IP version 4 or 6 for IP version 6. There's the header length, which is the number of bytes of the IP header. And so after all the IP header here, that data is the encapsulated segment from the transport layer above that sent its segment into the network layer. And so this portion, that top portion above the data section, all of that is network layer header information. So we have the header length, and that's used to count the number of bytes of this IP datagram, which is header information for the network layer. Then we have the type of service. We have the max number of hops. Now, this max number of hops, or the time to live field, every time a datagram reaches a router, that router, one of the things it does is it examines the header information, takes the TTL field, decrements it by 1, and then transmits it across the switching fabric to the output port. Now, certainly, once this time to live field is set to a specific value, once it goes to 0, any router that encounters it and sees that it's 0 is going to send back a response to say, oh, you know what, this thing is now invalid and I will no longer forward it. And the reason for that was back in the early days, you didn't want a datagram to go swirling around the network again and again and again from hop to hop to hop, this infinite datagram traveling around the network in an infinite loop, never to be seen again. And so they added this time to live field as a way of saying, okay, after visiting so many routers, if you're not at the destination after visiting so many routers, then just go ahead and get killed off. This upper layer protocol that describes to which transport layer protocol this is going to be, the payload is going to be delivered. It has a checksum. It also has a length field, which is the total datagram length in bytes, so the length of the entire datagram, not just the header field. And then we have some fields here that's used for fragmentation, and we'll talk about what fragmentation is in detail in a couple slides. So we have the checksum as well. We have a timestamp and other optional information. And so if we look at how many bytes correspond network layer header and how many transport layer header, you have 20 bytes for TCP that corresponds to transport layer header information, and then you have another 20 bytes, all of this information that corresponds to all of the network layer header information. So if you look at the application message, you have the application message plus 20 bytes of transport of TCP header information, 20 bytes of network layer IP information. So that's 40 bytes plus the application the application layer is the overhead. Okay, so we have 40 bytes of overhead total on top of the application layer data, for 20 from the transport layer and 20 bytes from the network layer. Okay, so let's take a look briefly at fragmentation. Now, fragmentation is the process of chopping up a datagram into smaller pieces because different networks might prefer different size datagrams, right? So on a host using a regular Ethernet network, you're going to have bigger datagram sizes, but let's say you have a hop along your network between the source and destination endpoint where you're going to go over, say, maybe a mobile network, right? And mobile devices would typically have smaller packet size because, they're wireless and deal with less intensity of the data that's sent back and forth. So networks have something called an MTU, a maximum transfer size, media transfer unit size, and a media transport unit size, or MTU, refers to the maximum size unit you can send across the network. And so the largest possible link layer frame, its header information is carved out of this MTU. And so different link types are going to have different MTUs or sizes of link layer frames that you're going to send across the wire. And so you're going to use some of this MTU for the link layer headers, as well as the payload, which is the network layer datagram. And then you can have 20 bytes for the network layer header, and then the rest is going to be the segment information for the transport layer, and then you're going to have 20 bytes of that for the transport layer header information, and the rest is going to be the application layer message. So different link types have different MTU sizes, and so a large datagram, when it encounters a hop that it has a smaller MTU, it's fragmented or broken up into pieces. Now these pieces are then sent as separate datagrams across that smaller MTU link, and they are not reassembled until they reach the endpoint destination. So MTUs are broken apart into smaller pieces, they're fragmented, and then each of those fragments is treated as a separate datagram and sent separately, and they only get reassembled at the endpoint. Okay, so large IP datagram is divided. When one datagram becomes several datagrams, you reassemble only at the final destination, and there are fields in the IP header, or the network layer header for Internet Protocol, that's used to identify and reorder all of the related fragments that started out from a message of a larger size. Okay, so you have an incoming datagram, and when it hits the router and gets ready to send it out the output link, the MTU is smaller, so it chops it up into 3 pieces, smaller pieces, such that it will fit within the smaller MTU size, and then send each one of those along the way, and then each of those 3 pieces makes its way to the destination and is reassembled into the original larger message using IP header information. Okay, so let's stop there, and next time we will pick up on Thursday with more of our conversation about this fragmentation